Namaste and welcome back to the Data Structures and Algorithms classes. Let us continue our discussion on time and space complexity. Now, it is the frequency count method which we were making use of. Now, let us solve few more examples to get a complete understanding of how to calculate your time complexities and especially the big O notation. Okay, let's start with our first example. Now our first example looks something like this, wherein I have a simple code snippet. Now if you look at this code snippet, few things must become very clear to you guys. That first and foremost, if you look at this condition here, this is what determines how many times looping is going to happen. And it is not i's value which is going to decide whether or not we're going to break out of the condition or not. It is actually p. How are you able to think? So you can't just directly tell that this outer loop is going to work n times. You cannot tell because I is not going to go from 0 till n. No, it is p's value which we are talking about. If in case you come inside, you will notice p, every time we are incrementing it by I. How are you able to think? So how are we going to analyze the time complexity or the big O of this? I hope you're able to think. Now how are we going to do it? Watch it and understand carefully. Let's try to trace the program. Okay. So first time i's value is 0. If i's value is 0, then if you ask me what is going to be p's value is going to be 0 itself. How are you able to think? Next, if i's value becomes 1, p's value will be whatever is the previous or the old value of p. Let us assume the old value of p is 0 plus I, which means 1. If I is 2, it will be the old value, which is nothing but 0 plus 1, plus I value, which is 2, because every time you're telling p is equal to p plus I. Similarly, if it is 3, it is the old value. And what is the old value? This is the old value plus the new value. So 0 plus 1 plus 2 plus the I value. Similarly, if in case I check this, till where will this I value go if you ask me? I will keep incrementing till the point where you come out of this loop. So let us assume that this will execute for, let us assume, k times. We'll just keep a constant value, we'll call it as k. Let us assume k times it will execute. We don't know how many times, so I'm calling it as k times. So if here it is k, then what will you write here? What you will write here is 0 plus 1 plus 2 plus 3 like that till k. Would you agree with me? Hence, when will this stop? When will you reach this value if you ask me? You will reach this value or the last value is reached when you break out of the loop. Now, what determines that you break out of the loop is nothing but when this condition becomes false. As long as p value is less than equal to n, you will loop. But the moment p value becomes greater, you will terminate. Would you agree with me? Which means, would you agree, one way for me to write it is, when will I break out of the loop, right? So maybe I can say like this, right? I can say something like termination. Termination condition, I will put it as. Termination condition. Now, what is going to be the termination condition here if you ask me? It is going to be whenever p value becomes greater than the n value. Less than equal to is fine, but the moment p value becomes greater than the n value, it will break out. So now, how am I going to analyze the time and space complexity if you ask me? Watch it carefully. First of all, look at this. The final value of p, which is going to determine this or where this condition is going to be satisfied, is this. How are you able to think? Which means p value is 0 plus 1 plus 2 plus 3 plus till k. Which means, don't you think it's the sum of k natural numbers? If it is the sum of k natural numbers, you already know a formula. What is the formula of k natural numbers? Sum of k natural numbers, k into k plus 1 divided by 2. If this is greater than n. I hope you're able to think. Which means, if in case I just multiply it, I will get something like this. K square plus k divided by 2 is greater than n. You know, whenever you analyze time and space complexity, you have to always ignore constants, which means the only thing this 2 can be ignored, which means this will become something like k square plus k is greater than n. You know, whenever you analyze time complexity, we will only keep the highest order term and remove lower order terms, which means k has to be removed, which means it will become k square greater than n, right? Now, till here I hope everybody understood. Now, let us assume I have k square greater than n. I want square to go. I want the square to go. What will you do? Whenever you want square to go, you will take the square root. I hope this basic mathematics you know. Which means on both sides, if I were to apply square root, then would you agree I can say k is greater than root n? Hope you're able to think. Which means whenever you analyze time complexity must be expressed in terms of the input size. And tell me, the input size is always determined by n. N is the input size, not p, not k, which means I should not express in terms of k or p. It is always in terms of n, and clearly one can notice that here the time complexity is root n, which means, wouldn't you agree, I can say that this is big O of root n. This, my dear friends, is the time complexity of this code. I hope you got a general idea of how we are calculating. So, if you look at this, one more thing which becomes very, very evident to anybody who's carefully looking at this is, we have seen n cube. Naturally, n cube will take more time than n square. Naturally, n square will take more time than n. Naturally, n is going to take more time than root n. So I hope you are able to see that, certain pieces of code are much more efficient than few other pieces of code. Any confusion till this point of time? I hope everybody understood how I analyze the time complexity of this. Let's go check out few more code snippets, shall we? This is the next one which I would like to analyze. If you look at this, there are some statements inside, it doesn't matter to us, but I value begins from 1. Yes, it is I less than n only. So you will immediately tell, oh, it is going to be n times, sir. No, you can't analyze it that way, because look at the step size, look at the incrementation. The incrementation is happening by multiplying the existing value of I by 2. So every time into 2, into 2, into 2. So it is definitely not going to be big O of n. So how are we going to analyze something where every time the step size is into 2? You're doubling it, you're doubling it, you're doubling it. So how are you going to analyze? Very simple. Let's begin, alright. So first and foremost, if you ask me, whenever I value is 1, right? Whenever I value is 1, I can say that it will become, first time it is going to become 1 into 2. Second time it is going to become 1 into 2, that is the previous value, into 2. Next time it will be 1 into 2 into 2, that is the previous value, into 2. Next it will be 1 into 2 into 2 into 2, that is the previous value, into 2. So it is going to continue like that. A more simplified form would be, I can write this as 2, I can write this as 2 to the power 2, I can write this as 2 to the power cube or 3, I can write this as 2 to the power 4. Would you agree that this is one way for me to write it? Like this, let us assume I value keeps incrementing till you come out of the loop, And the last value of I that made you come out of the loop, would you agree that I can write it something like this, where I can write it as 2 to the power k, because we don't know how many times, so I'm putting some constant called as k. Any confusion till here? Now the moment I value becomes 2 to the power k, it means that this condition became false. This is the last value, that's why it came out. Which means, would you agree, 2 to the power k is not going to be less than n. 2 to the power k is going to be greater than n or equal to n. Only then it will come outside. Which means, I can write it this way, that 2 to the power k is greater than or equal to n. This in a way is my termination condition. So I am just writing it here. This is my termination condition. Any confusion till here? 100% everybody would agree that this is my termination condition. Yes sir, you're absolutely right. So now see, I'm going to start analyzing the time complexity. Okay. Now I want, so I have 2 to the power k greater than or equal to n. Which means in one way I can write 2 to the power k equal to n. Let's remove that greater than. I want k value, I want in terms of k, I want this k which is in the power to come below. Whenever you want something in the power to come below, you have to apply log on both sides. This is simple mathematics which you have learned in your first PU, second PU, 11th standard, 12th standard. Just refresh your mind a little bit, right? Which means, don't you think I can write this as log, okay, 2 to the power k is equal to log n, like this I can write. Now the question is, different logs comes with different bases, right? Base 2, base 10. Now what is the base here, you must be wondering. It's very simple. Look at this. This is the base. What is the base? 2, 2, 2, 2. So naturally you have to, whenever you apply log, you here, because the base is 2, you will be applying log to the base 2 like this. Now if I just expand it a little bit, it will look something like this. I will get k log 2 to the base 2 and I will get log n to the base 2. Everyone knows log 2 to base 2 is nothing but 1, which means this is 1. This is 1. If this is 1, I will get k equal to log n to the base 2. Hope you are able to think. Which means maximum, how many times will it execute? These many times. And hence, would you agree, one way for me to tell this is nothing but big O of log n to the base 2. However, you must understand, if this was into 3 friends, if this was, let us assume, I equal to I into 3, then wouldn't you agree, every time I could have expressed it as a power of 3, 3 square, 3 cube, 3 to the power 4, 3 to the power k. Which means here, which log you would have applied? Log to the base 3 you would have applied. Are you able to think? Similarly, anything, if it was 4, log to the base 4, 5, log to the base 5, that you could have applied. Which means, whenever you express time complexity, usually we do not represent constants as such. You can always represent it this way, or you can also represent it this way. Both are one and the same. You can always express it as big O of log n. So do you see, you have seen log n complexity. Now tell me, n cube, n square, n root n, lesser than root n, obviously is log. I hope you're able to think. Any confusion till this point of time? So how we analyze this is also clear to everybody. Great. Let us analyze one more code snippet. Watch it. Now, this is the next one I would like to analyze. This is the statement I have. I begins from n. From n till 1 it goes. Every time I value, I am dividing it by 2. Every time the value of I am cutting it by half. I am dividing it by 2. What could be the time complexity of such a piece of code? Very, very simple. Listen and listen carefully. I am just analyzing this for you. Now, would it be fair if I said that this loop is going to execute for as many times, as long as this I value is going to be greater than or equal to 1, the moment it becomes less than 1, my loop will stop. So what is that value of I for which it is going to become less than 1? We do not know. But let us see how the I values are going to change, right? So first time the value of I is n. Second time the value of I is going to be n divided by 2. Next time the value of I is going to become n divided by 4. I can write it as n divided by 4, or would it be fair for me to say I can write it like this also? Next time, would it be fair for me to say that I value will be this? Like that, don't you think I can generalize and say that it will become n divided by 2 to the power k, because we do not know how many times, but we know k times. We do not know how many times, it depends, k times. So the moment I value becomes n divided by 2 to the power k, its value is going to be less than 1 and you're going to terminate. So this is the maximum number of times your loop is going to work. As I've told you, whenever you're analyzing this loop for statement, always all true values plus the one false value also you have to analyze. And that is why I'm looking at that value which makes it as false, because that also should be included. So now this is how I have got it, which means now in one way is I can write it like this. Can I approximately tell n divided by 2 to the power k is equal to 1, right? If it is equal to 1, then I can write it as n is equal to 2 to the power k. Again, don't you think I can apply log on both sides? Now, naturally, I have 2 to the power. I would like to apply log on both sides. If you apply log on both sides, I think everybody knows this will become log n to the base 2, and this will become k log 2 to the base 2. This is naturally going to become 1, which means I will get log n to the base 2 is equal to k, and time complexity is always expressed in terms of input size, which means what we are going to be getting now is a time complexity of log n, and this is optional. The base 2 is optional, log n. I hope the way we have analyzed it is clear to everybody. Now let's go ahead and analyze the next one, but before that, something interesting you are seeing here. Whenever I'm doubling the step, right? The first time, the second time is like if I double it, into 2, we will get logarithmic. If I cut it by half, you will get logarithmic, and it's with common sense. See, let us assume I value was 16. Now from 16 till 1, there are 16 numbers. But you are not iterating over all 16 numbers. What you will do is 16, then half, 8, then half, 4, then half, 2. So obviously, it will be more efficient, and you can see that in terms of the big O as well. Anyways, let's analyze the next one. Okay, the next one looks something like this. Watch it, guys. I begins from 0. Every time square the value of I, check if it is less than n. If so, execute the statement, increase the value of I by exactly 1. Which means, would you agree, I can say I value increases like this: 0, 1, 2, 3, 4, 5. Now, I do not tell where it will go, but I can in general say that it will go till k. Now, every time you are checking a condition, which is if I is 0, 0 into 0, which means I can say like this: 0 square, then 1 square, 2 square, 3 square, 4 square, 5 square, like that. If you ask me, for the kth value of I, where termination will happen, what is going to be the value of I? I don't know. But I know it is going to be a square of whatever is the value of I, which means in general, I can tell I is square. Now, what does this mean? This means that termination condition is, if at all the value is k, this k value becomes greater than or equal to n, because the true condition is for less than. So either greater than or equal to n. K, that kth value we know is nothing but the square of whatever was the I value, which means, don't you think I can write this as I square is greater than or equal to n? Now, don't you think whenever you want to remove the square, what do? Apply square root on both sides. So I can tell square root of I square is greater than or equal to square root of n, which means this will become I greater than equal to n. When will you, how will you, based on what will you represent the complexity? Always in terms of the input size, right? And this is root n. I missed the root n. So what is the time complexity here? Big O of root n, which is what I am also just showing. I hope you're able to think. So somewhere you're noticing that whenever in your looping statements, if there is squaring happening, some form of squaring happening, it's always root. When it is being doubled or cut by half, it is log. When it is just linearly increasing, it will be n. If there is a nesting of a loop, then n square. If there is further nestings, then n cube, n to the power like that k, whatever it can keep going. So you're able to see some patterns here. So every time we will be solving some kind of a problem related to data structures and algorithms, we will use an approach, whatever approach comes to our mind, and we will analyze the complexity of the approach. And if the complexity is very bad, then we are going to think about new and novel approaches towards solving the problem in a more efficient way. And that is the journey of data structures and algorithms. And that is why these product-based companies expect you to know it. Any confusion till here? Great, we have analyzed this as well. Let's go to the next one. So the next one, this is the code that I have. Now I want you to look at this. I is starting from 0. I is going till n. There are some statements executing. This is a separate loop outside that. J is starting from 0, J is going till n. Which means, you know, whenever it goes from 0 to n and is just incrementing one by one, you know this is a linear time complexity. We have already seen a code snippet like this, which means, wouldn't you agree, the time complexity of this code, is nothing but your big O of n. Wouldn't you agree that the time complexity of this code is also nothing but big O of n? So this is big O of n, this is big O of n. Combined you want, combined. Combined means what? Plus. N plus n is what? 2n. Should you have your constants within your time complexity? No. Which means remove this. Remove this. And just tell n. Hence, what is the time complexity? Big O of n. I hope you're able to think. Which means it is not like it is going to be 2n or n square or anything. Even here it is n. Worst case, it is going to execute n times. That is the concept here. So it is big O of n. Any confusion till this point of time? Yes, great. What else you may ask? Next one looks something like this. Here also there are two loops. They are, you know, different loops. It's not like one is inside the other. If you look at this loop, I begins from 1, I goes less than n, I increments by 2 times every time. And there is a p value which I have initialized to 0, and every time the condition of the loop is true, this p value is incrementing. Which means one way to say it is, how many times will this p value increment? It will increment as many times as this loop works. Would you agree with me? Which means, tell me, I starts from 1, I goes till n, every time it's doubling in value. Tell me, will it be n, n square, n cube, or is it going to be logarithmic? Obviously it is going to be logarithmic. We have seen that whenever you're doubling or cutting by half, it is always log. So, don't you think that I can easily represent the time complexity? I can easily represent the time complexity of this particular loop as log n. Base 2, sir? Yeah, I know that, but I'm just writing it as log n. Any confusion till here? Also, one thing for you to understand is, this p value also how many times it will execute. If you analyze the complexity of this statement, don't you think this statement is also log n only? Log n times. How many times it will execute, that many times it will increment. So it is log n. Now I am coming here and see what is happening here carefully. Whatever is the value of p that was computed here, that is the value of p which you are assigning here, my dear friend. Are you able to notice that? Which means this j begins from 1, but it doesn't go till n, it goes till p. And this p value is, you have got it from here. And see, here also it is into 2, into 2, into 2. It is increasing, which means what is going to be the time complexity here, right? So if you look at it, here n is the input size. So in terms of n, you wrote log n. Here p is the input size, which means you are going to calculate it in terms of p. And if I calculate it in terms of p, would you agree that here I can say that this is log p? Why? Because every time j value is doubling, so log p. Are you able to think? Now, in general, always in terms of n only you must write the complexity, which means I don't want this p. So can I substitute any value for p? 100% I can, because I told you the number of times p will execute or the number of times it will increment is nothing but the same as this log n. How many times this loop will work, that many times it will increment. Which means, don't you think I can replace this p with log n? And hence, would you agree that I can write it this way? I can write it this way, where I can tell log p, I will replace it with this. So it will become log of log n. How are you able to think? So log of log n is your time complexity. How are you able to think? Because this is also logarithmic. Whatever value was computed here is being substituted here, and this loop is also logarithmic. So log of log n. Did you understand how to analyze it? Don't worry. It is through practice, it is through consistency, and it is through experience that you will be able to get it. So now what will happen is, as you keep spending time with me, there will come a point where you will just look at a loop and you will be like, oh, okay, so this will be logarithmic. Oh, this value is being used here. Oh, this is also logarithmic. So log of log n. Tuck, you will tell. No need to do all this drama. But it will come with time. It will come with practice. You must have patience. Okay? Great. Next what? Next, this is the code snippet in front of me. Let us look at this. Clearly there is nesting here. Clearly there is nesting here. And obviously whenever there is nesting, it is better that you use this frequency count method. It will make your life easy. Easily you will be able to analyze. Now, if you look at this, one thing that I can say for sure is this loop begins from 0, goes till n, right? Plus plus, 1 by 1. So it's going to be linear. It's going to be linear. So I know this will execute n plus 1 times. We know that. N is n times for true, n plus 1 is for the false. Which means this will execute n plus 1 times. If this will execute n plus 1 times, whatever is inside it will execute 1 time lesser, which means I can tell n, I can tell n. Here, if you look at this, you are within another loop, so you must analyze 1 till n, but it is jumping by 2, it's doubling. Whenever it's jumping by 2, or whenever it is getting cut by 2, we know it's logarithmic. Which means, don't you think this time complexity of this, or the number of times it will execute, I can directly tell is log n. Whenever you have two terms, in between you must apply multiplication. If this is going to execute log n times, don't you think this statement inside it is going to execute 1 time lesser, which means I can tell log n minus 1. And whenever there are two terms, put a star in between or multiplication, add all of them together. This minus 1, okay, so basically we can remove all these constants, and if I do that, I will get something like n plus 2 into n into log n, like this. Would you agree? N into log n. Again, let's remove the constant, which means I will get n plus n log n. I have n log n, which is a lower order term. Which is a lower order term? Obviously, it is n, because we have n into log n. Obviously, this is a lower order term. Remove that. And hence, your time complexity is in a very straightforward manner defined as big O of n log n. And if you look at it, it's so intuitive to analyze. There is nesting. Outer loop n times. Inner loop log n times. N log n. I to n, I plus plus. Here also j 1 to n, but j into 2. Logarithmic, linear. Any confusion till here? N log n is your time complexity. Any confusion till this point of time? Great. Yes, sir. We understood. So, I hope these few code snippets have given you the much deserved clarity. But we are not going to stop here. In the next part of this session, I am going to be speaking about few more code snippets, and after that you would have seen almost all types of time complexity. And then when we start doing our problems on arrays, on linked lists, on trees, on graphs, questions from all your top FANG companies, you will easily be able to analyze whether the code written is efficient or not. Anyways, see you in the next class.